Greetings. This is the review for the forthcoming midterm. So the midterm is online. It's 8 to 8:30, although it'll typically open at 7:55. It's during class times on Monday, Wednesday, and Friday, all 3 days, for a half hour each day, and it's accessible through Canvas. There is a test exam or practice exam on Canvas. I encourage you to do that just to be familiar with the protocol. It's in class time during week 6. I encourage everybody to look at the practice exam and also the previous exams, as we've talked about in class many times. And it's not supposed to be a problem in terms of the functioning of the exam. If you have a problem sending it, or if you get cut off when it closes at 8:31, which it will do for submitting your answers, just send your answers in an email directly so that they arrive quickly, either to myself or Shinshin. Myself is probably the easiest one to remember, but get them in quickly because obviously we don't want to give people some extra chances based on extra time. The material covered is everything up to 4.1. So we cover fluid properties, which we talked about in week 1. We talk about fluid pressures at a point, which was our week 2 material. Fluid pressures acting on structures, which was basically week 3, and also buoyancy. And then finally 4.1, which is a new week's topic, but the first Monday's material was relevant in terms of accelerating static fluids. There are 3 questions. Those 3 questions are different on the Monday, Wednesday, and Friday. There'll be this, the material for those individual questions is as shown here. Ideal gas law on Monday, pressure at a point, and concepts of buoyancy. So you can probably make a decent guess about what that might be. And certainly you can look at the previous exams to see what those have been in the past. The Wednesday test is on fluid pressures acting on structures, week 3 material, and the Friday midterm is on viscosity. So that allows you to at least hone your choices on what you'll look at. I typically go through the equations that you would need. I make no guarantees that these are the only equations you'll need, but if you check on previous exams, you'll see that they pretty much are the only material that you need. Equation of state, you need to know the ideal gas law. You need to know that the ideal gas law is written in terms of absolute pressures, absolute temperatures, and a gas constant which depends on the gas that you're talking about and relates to a density. You can also write the density as a mass per unit volume, which is useful sometimes if you have an enclosed mass within a bubble or a balloon and the balloon shrinks, the mass won't change. And you can also write it in terms of the ratio of the universal gas constant, R bar, divided by the molar weight of the particular gas. So those are different ways of writing the ideal gas law. If you're looking at a bubble or a balloon, then you can do a free body diagram that defines the force acting upwards, the buoyant force, relative to the force acting downwards, which is the weight of the system, and it may be a tether if it's a buoy that's attached, for instance. For a bubble or a balloon to rise, then the density of the balloon or the interior has to be less than the density of the exterior, and it's this difference in density that provides the buoyant force. If it's a liquid on the outside and air in the inside, then the difference between 1,000 kilograms of cubic meter and 1 kilogram cubic meter is usually so much that you don't even have to consider the internal pressure, internal density. But if it's a balloon, for instance, with air outside and a slightly less dense air inside, then you do have to include this as the weight of the balloon. So you can either include it as a weight of the acting vertically as the weight, or you can look at the difference in the buoyancies in the buoyant force. And so if you want to look at something that will rise, you can write the ideal gas law in terms of the density. And if you do that, then either for it to rise, to reduce the density, you either have to reduce pressure, increase temperature, or increase the gas constant by changing the gas that's in the balloon. A helium balloon, for instance, instead of an air balloon. Also in fluid properties, we talked about viscosity. Viscosity, Newtonian viscosity, is defined by Newton's law of viscosity, which says that the shear stress that you apply is proportional to the velocity gradient in space. The rate of change is the velocity in the x direction in this particular case, how it changes in the y direction, which is what this term is here. And the constant that relates the shear stress to that gradient in velocity is the dynamic viscosity, which has units of Pascal seconds, which are also newtons per meter squared times seconds. Pascal is just a newton per meter squared. The geometry of sliding plates that we've looked at defines the shear stress moving at some velocity on a rigid plate. The shear stress divided by the area of contact at this plate defines shear force. So these are linked with each other. Usually this gradient you take as a linear gradient, and it defines the viscosity of this fluid, just as the ratio of this curve. And of course you can write a free body diagram, and if you take a free body diagram that cuts this, then you'd find out that the shear stress that's acting on any point that you cut off within this section is going to be the same shear stress, just from the free body diagram. And so you can use that to solve some problems. We've talked about fluid pressures at a point. We know that for fluid pressures at a point, this expression here always holds and says that the change in pressure with elevation is always equal to the minus value of the unit weight of the fluid. This is always true, both for an incompressible liquid and a compressible gas. If you integrate this to be able to come up with an expression that gives you the pressure distribution as an algebraic expression, then we get different expressions if you integrate for a compressible fluid, because the fluid above you changes density as the pressure changes with elevation, or for an incompressible fluid which is constant with depth because it doesn't change density. If you integrate this expression for an incompressible fluid, then you get an expression that looks something like this, that says that the fluid pressure at a particular location is equal to the fluid pressure you have acting at some other location, plus an elevation difference to get to that, multiplied by the unit weight. And you just have to be mindful of what this sign is as whether you're going up or down. And so that's probably the easiest way to calculate how pressure changes with elevation for a compressible fluid. And it just comes from integrating this expression. We know that you go horizontally within a fluid, the pressure doesn't change. We use this a lot in the manometry equations as kind of a standard result. The consequences, I guess, for a gas being compressible is that if you look at the change of pressure with depth for an incompressible fluid, it varies linearly with depth. But for compressible gas, we know that it asymptotes to from atmospheric pressure here, which is roughly 100 kPa. It asymptotes to 0 kPa atmospheric as you go up into space. And of course, if you draw this to scale, then the geometry of this graph is such that if this is pressure and this is elevation, then below the fluid it varies like this, because this is 1,000 kilograms per meter cubed, and above here the density of water is about 1 kilogram per meter cubed. So the ratio of these gradients is 1 to 1,000. So it's basically not changing in the same way. It's not that it's not changing. It's not changing as quickly as in the liquid. We've used manometry. I guess manometry isn't noted in the questions above, but just what we do in manometry is if we go up, we reduce pressures. If we go down, we increase pressures. if the fluid is a gas, then essentially no change in pressure as you go up in a gas because of its very low density compared to the fluid which we're measuring otherwise. And I guess we have to be mindful of absolute pressures and gauge pressures in being able to do that, mainly because if we define vapor pressures are typically defined in terms of absolute pressures. But as I said, I think there is no manometry question in the things we're talking about. Pressures on structures, we do that by using two expressions. The first expression is to define the magnitude of that force. The magnitude is always given by the unit weight of the fluid, the depth of the centroid below the surface, and the area of the plate. And so that's represented here for an inclined plate. The depth of the centroid is the center of gravity, if you like, of the plate, which is the middle of the plate in this particular case, and its absolute depth relative to the surface. The area of the plate would just be the area of the plate surrounding this. Included in this blue part, this would be the area, and the unit weight would be the unit weight of the fluid that surrounds it. It's important to note that the point of action of that force does not occur at the centroid, but it occurs at the center of pressure. And the center of pressure we can get from the magnitude of this YR. YR is always measured inclined from where the surface of the fluid, where the projection of the plate intersects the center of the fluid, and the depth of the centroid is the slope distance to that point. And that slope distance is equal to the slope distance of the depth of the centroid plus a small amount delta YC, which is given by this term here. And it's the second moment of area about the centroid, which is a standard result. I think it's depends on what it is. It's something like a 12 b squared a or something like that, or similar expressions, not similar to this. It's equal to the slope distance of the depth of the centroid below the surface and also the end of area of the plate. So this, if you know this value here, you can calculate both of these terms and you come up with YR. This is the point at which the pressure will act. So if you need to find that out and take moments about that location, you can do that. That allows you to find the point of action. If you're asked then to look at, say, a mode of failure, then maybe you have to take moments around a particular hinge point. And if you want to take moments around a hinge point, you need to find the distance of the lever arm or the length of the lever arm relative to the force that's acting. And those magnitudes are given by whatever this length is, not necessarily YR, right? But the magnitude of this resultant force multiplied by the lever arm. And so you can always calculate the moment from that. For these failure modes, not an uncommon way of looking at these problems. The other way that you can divide this up is to look at the pressure distribution on a structure, in this case a gate which is able to rotate, and you can divide that pressure distribution into two parts. You could take the pressure at this point here and draw this trapezoid, which is just a distribution of that pressure. You could also take the pressure at this point, which gives you this magnitude here, and that would give you this distribution of pressure. And if you wanted to calculate the magnitudes of the relative lever arms for this entire distribution, the true forces acting on the system, then what you'd do is you'd take moments around a particular point, which would be the force of the square area multiplied by its length of action relative to a point, the force due to the triangular distribution relative to its length of action relative to this point, which would be this magnitude here, and equate that to the total force, which would be the sum of F square and F triangular multiplied by its lever arm. So in each of these cases, you'd know this, you'd know this, you'd know this, and you'd know this. And the only thing that you wouldn't know would be this particular lever arm in this particular case. So that would be the one way to be able to determine that. For buoyancy, buoyancy relates to the force that's applied on the structure. In general, the buoyant force is equal to the unit weight of the displaced fluid times the volume of that displaced fluid, or the unit weight of the displaced fluid multiplied by its volume. Typically, you're taking a force balance, which is the buoyant force acting in the direction opposite gravity, multiplied by the weight of something acting in the direction of gravity, and you can do a force balance. If this is submerged below a liquid, then it's probably adequate to take the density of the interior as equal to 0 and take the density of the liquid as being the magnitude of this that you use in this calculation. However, if you're solving a system where it's a balloon, then it's probably not appropriate to take this buoyant force acting inside this as 0. And if you do that, the easiest way to do it is to do it equivalently in terms of taking the buoyant force as equal to the difference in the densities, or the unit weights, of the external fluid and the internal fluid. And that would give you the correct buoyant force. And then you would only have to include a weight of something attached to this structure, if it's a balloon, to be able to do the calculation. And so you need to be a bit careful about how you handle the buoyant forces in all of these. And the reason for the buoyant force being equal to the displaced fluid multiplied by the volume is that if you take the fluid out of this, you have an imbalance between the pressure acting downwards and a larger pressure acting upwards, and this larger pressure acting upwards is the magnitude of this buoyant force. So I think those are the key things that you need to be able to do to be able to show your best in the midterms, again, which occur on each of the 3 days, the 3 mornings of week 6 in this particular time, with the topics here. And I encourage you to look at the previous exams to go specially through topics which relate to the ones that will occur on this particular exam. Okay? Great. Good luck. Good luck in showing your best